In this video, we discuss the mean value theorem. It is a generalization of Rolle's theorem. Basically, remember we had Rolle's theorem. We discussed Rolle's theorem in the last several videos. Rolle's theorem said that if f is continuous on a closed interval a to b and differentiable on an open interval from a to b, and the y values are the same at the endpoints, then there's at least one x value on the interval where the derivative is equal to 0. So the fact that it's continuous means that we can draw it with one curve from this location to this location. The fact that it's differentiable means that that curve is nice and smooth. So if we're starting at one y value here and then we're ending at the same y value, if we go up, then we have to come down. If we go down, then we have to come up. So we're guaranteed to have that point where the derivative is 0 because the function's differentiable. And that point where the derivative is 0 is guaranteed to be a relative min or a relative max, or we're guaranteed at least one of those, because if the function goes up, then it has to come down, or if it goes down, then it has to come up. The mean value theorem is very similar, except we don't have this requirement anymore. We say, well, if the function's continuous on the closed interval from a to b and differentiable on the open interval from a to b, well, what can we say about the derivative on that interval? Well, the mean value theorem says that there exists at least one x value on that interval where the derivative at that x value is equal to the slope of the secant line. Remember when we talked about instantaneous rates of change and average rate of change, this is the average rate of change of that function on the interval from a to b, and this is the instantaneous rate of change of the function on the interval from a to b. And the example that I always think of is like speeding. Whenever you are driving down the highway and the cop has one of those, I don't know, the sensor things, I actually don't know how that works at all, that determines what your speed is, all they're getting is your instantaneous speed or your instantaneous rate of change. What this theorem says is that there has to be a point when your instantaneous rate of change equals your average rate of change. So if you go a certain number of miles in a certain amount of time, your average rate of change is a fixed value. Now, even if you slow down whenever there's a cop nearby, if they know your average rate of change because they're able to figure out how far you've traveled in a certain time interval, even if at that moment you're not speeding, they can infer that you had to have been speeding at some point on the interval if your average rate of change exceeds the speed limit. So that's one application of the mean value theorem. But basically, the idea is the instantaneous rate of change there has to be at least one point where the instantaneous rate of change equals your average rate of change. If the y values at the ends are the same, well, then this numerator is going to be 0. Your average rate of change would be 0. So then we'd have Rolle's theorem. But if the y values at the endpoints, the point where you start and the point where you end, are different, then we can generalize that in this way. So that's the idea. So it's almost identical to Rolle's theorem, except we're no longer requiring that f of a equal f of b. Now we're saying f of a and f of b can be any value, but we still need the function to be continuous on the closed interval from a to b and differentiable so that it's nice and smooth on the open interval from a to b. Okay, so let's apply that in a specific example. We've got y equals 5 minus x squared, and let's look at it on the interval from -2 to 2, and then on the interval from -3 to 1. Well, 5 minus x squared is just a parabola. We multiplied it by -1, so we flipped it upside down, then we added 5 to it. And roughly it looks like this. And that'll equal 0 when x equals plus or minus the square root of 5. So this is a positive square root of 5, and this is a negative square root of 5. If we're on the interval from -2 to 2, we're just talking about this part of the graph. We start here and we end here. And we've got this parabola right here. Now this is a good candidate for Rolle's theorem because if I evaluate the function at -2 and 2, I get the same y value. Y evaluated at -2 is just 5 minus -2 squared, or 1. And y at 2 is the same thing. We also get 1. So our average rate of change is y of 2 minus y of negative 2 divided by 2 minus negative 2. And I'll just say average rate of change. And it's just going to be 0 divided by 4, or 0. So this is a good candidate for Rolle's theorem. Now, remember what we say, we can only apply these theorems if the function is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Well, this is just a polynomial, so of course it's continuous and it's differentiable. And that's going to be true on any interval starting with a particular finite number and ending with a different particular finite number. So the question is, does the mean value theorem apply? Yes, it does. And of course, we're looking at the special case in this example where the average rate of change is 0. So that's actually a Rolle's theorem, which is a special case of the mean value theorem. So let's say y equals f of x is continuous and differentiable on the interval from -2 to 2. So the mean value theorem applies. And then it says, if so, find the x values guaranteed to exist by the theorem. Well, that means there are some x values out there where the instantaneous rate of change equals the average rate of change. So we just need to find f prime, set it equal to the average rate of change, and then solve for x. So we have the derivative with respect to x of 5 minus x squared, which is just the derivative of 5, which is 0, minus the derivative of x squared, which is -2x. We set that equal to the slope of the secant line, or the average rate of change, which in this case is 0, and then solve for x, so x equals 0. That is the x value that satisfies the theorem. Now, geometrically, in this case, what we're talking about is we're finding a location, an x value, where the secant line is parallel to the tangent line. The secant line just passes through those 2 points. And in this case, it has the equation y equals 1 because it's horizontal. The slope of the secant line is equal to the average rate of change, and it's 0. And they're saying, okay, well, where is the slope of the tangent line equal to the slope of the secant line? It's going to be equal to the slope of the secant line, the slope of the tangent line will be equal to 0 at the top here. So that's y equals 5. That's the tangent line at x equals 0. Okay, so that's what the theorem says. Now, one other thing I want to point out is that it says, let f be continuous on this closed interval and differentiable on the open interval from a to b. Then there exists some x value such that this is true. And I guess we should say, I'm not going to just say some x value. Let's say at least one x in the interval from a to b, such that this is true. Now, it's possible that instead of having a parabola where you just have one x value that looks like that, you could have more than one x value. And of course, this is a Rolle's theorem example, but it's also possible that on a different interval, rather than having y values that are the same, we're going to have y values that are different. So we can illustrate that on the interval from -3 to 1 for this function. So this was part A. Part B, we have y evaluated at -3 is 5 minus -3 squared. So 5 minus 9, which is -4. And y evaluated at 1 is 5 minus 1 squared, which is 5 minus 1, or +4. So we're still dealing with this parabola. When x equals 0, y equals 5. When x equals 1, y equals 4. When x equals -3, y equals -4. And that is our maximum there, and there's some symmetry. So we're going to go down 1, and then go down 1 and to the left 1 and down 1 to the right 1. And then we'll go left 2 and down 4. So at x equals -2, we should have a 1. And so this is the part of the parabola that I'm interested in. Excuse me. Now, the slope of the secant line, also known as the average rate of change of the function on the interval, is y evaluated at 1 minus y evaluated at -3 divided by 1 minus -3. And y evaluated at 1 was 4, and we're subtracting -4 from that. And then we're dividing by 1 minus a -3, which is the same as 1 plus 3. So we end up with 8 divided by 4, or 2. If we want, we can graph that line. So here's our secant line. And in this case, the secant line has a slope of 2 for this particular interval. And now the question is, well, where is the x value where the slope of the tangent line is equal to 2? And first of all, does the theorem apply? Yes, it does, because the function is still continuous and differentiable. It's just a parabola when we graph it. It's nice and smooth. We can draw it without picking up our pencil. So the theorem applies. Now we have to find the x values where the derivative is equal to the slope of the tangent, or the secant line, or the slope of the tangent line is equal to the slope of the secant line. So to do that, we compute f prime. So we have y equals f of x. I'm just calling it f now so that it has a name. And then y prime or f prime of x, either one is fine, is equal to -2x. And then we set f prime of x equal to the slope of the secant line and solve. So I've got a -2x equals the slope of the secant, which in this case is 2. Divide both sides by -2 to get x by itself. We have x equals -1. So when x equals -1, the slope of the tangent line should be equal to the slope of the secant line. And if I substitute -1 into this, I have -2 times -1 is +2. So the slope of the tangent and the slope of the secant are the same, so that's cool. And then the equation of the tangent line is y equals the original y value at that x value plus the slope at that x value times x minus that x value. So this is change in y divided by change in x times change in x. That's going to give us a change in y. That change in y plus the original y value, or plus the original y value, is the new y value. So this turned out to be 2. And subtracting a -1 is the same as adding 1. And f evaluated at -1 was 5 minus a -1 squared, which is 4. So we've got 4 plus this expression, distribute your 2, collect like terms, and we have y equals 2x plus 6. So here is 6. And we would use rise over run to find another point on the lines. We'd go up 2 and over 1. We can also go down 2 and over 1, find another point on the line. And if I draw my lines correctly, and if my grid was to scale, we would see that this line is parallel to this line. So it's super easy. At this location, x equals -1, y equals 4. The slope of the tangent line is equal to the slope of the secant line over the entire interval. So the average rate of change, which is 2, is equal to the instantaneous rate of change, which is also 2, when x equals -1. And -1 is on the interval from -3 to 1, which is what the theorem says. It says there is at least one x value where that instantaneous rate of change or slope of the tangent line is equal to the average rate of change or slope of the secant line. Same thing. All right. So that's the idea. Now let's look at that on Desmos. Well, actually, we'll do one other example with a polynomial first. Now for this function, we've got another polynomial. It's very easy to differentiate. We know that polynomials are continuous and differentiable on their domains for all real numbers. So the mean value theorem certainly applies. We just have to find the function values at -3 and 2. And I'll choose to label this y equals f of x so that we can use function notation. We have f of -3, and then we'll evaluate f of 2. And so we get -27 plus 21 plus 9. This gives us 30 minus 27, or 3. And then if we evaluate at 2, we get 8 minus 14 plus 9. Oh, we get 3 again. And so that is another Rolle's theorem example. Here, the slope of the secant line is f of 2 minus f of -3 divided by 3, or 2 minus -3. So we get 3 minus 3 divided by 5, which is 0. And the slope of the secant will equal the slope of the tangent when, whenever f prime is equal to 0 in this case. So first we need to compute f prime. I think we did this before in the Rolle's theorem examples. And then we set that equal to the slope of the secant. In this case, that's 0. And then we solve for x by adding 7 to both sides, dividing by 3, and then taking the square root. We get two values. I feel like they were approximately 1.5-ish, plus or minus 1.5. On this interval, we actually have both of those x values. So at both of those locations, the slope of the tangent line is equal to 0, which is equal to the slope of the secant line over the entire interval. But if we change those values, then what we get is something where the mean value theorem applies. Now, one of the things I want to point out before we look at this example or similar examples on Desmos.com is that this picture and this picture are actually very similar. It's almost as if we took this picture and we sort of drew it on its side. Like here, the tangent line and the secant line are parallel. Here, the tangent line and the secant line are parallel. Just in this case, our secant line has a non-zero slope. In this case, our secant line has a 0 slope. So that's really the difference between Rolle's theorem and the mean value theorem. With Rolle's theorem, the y values are always the same on the ends, so the average rate of change is always 0. With the mean value theorem, we allow ourselves to have a different slope of the secant, a secant slope that's non-zero. But in either case, the theorem says that if the function is continuous and differentiable on the closed interval from a to b and then the corresponding open interval, then we're guaranteed at least one point where the x value, there's an x value where the slope of the tangent line is equal to the slope of the secant. Now, in this example, because it's a cubic polynomial, rather than having one x value, we actually end up with two x values. And that just happens to be the case for this particular example, because when I solve this equation, f prime is equal to m secant for x, well, it's a quadratic equation. It has two solutions. Now, even if that slope of the secant was some non-zero number, we would still add 7 to both sides, divide by 3, take the square root, don't forget the plus or minus, and you would get 2 results no matter what. So in general, let's say m secant is just going to be f of b minus f of a divided by b minus a. And then to find the points of interest, we set f prime equal to m secant. In this case, 3x squared minus 7 equal to m secant. And then you can solve for x by adding 7 to both sides, dividing both sides by 3, and then to get rid of the squaring function, you take the square root. Don't forget the plus or minus. So for this function, you get 2 values. Now you might not always have those 2 values on the interval of interest. The intermediate value theorem, or excuse me, the mean value theorem says you are guaranteed at least one of those values on the interval of interest. But we might get 2. We might get both of them. It really just depends on how large that interval is. So let's look at these 2 functions on desmos.com to illustrate the idea of the theorem. Okay, so this was our first example. We had y equals 5 minus x squared, and we're interested in it on the interval from a to b. Now, initially I let my a and b be -2 so that the y values are the same. Then Rolle's theorem applies. So if we wanted to, we could graph the secant line. The slope of the secant is f of a minus f of b minus f of a, that's a change in y, divided by b minus a, that's a change in x, just change in y over change in x as usual for any slope. We can graph that secant line right there. And the theorem says that because this function, which is just a quadratic function, is continuous and differentiable on the interval of interest, this interval from -2 to 2, then there's at least one x value on the interval where the slope of the tangent line is equal to the slope of the secant line, or alternatively, the instantaneous rate of change of the function is equal to the average rate of change of the function. So basically, I'm just looking for an x value where the tangent line is parallel to this one, and this line happens to be horizontal. So to find it, we compute the derivative. The derivative of 5 minus x squared is -2x. If we want, we can graph it like this. And then we can see, well, the derivative is 0, then that's equal to the slope of the secant, when x equals 0. So if we want to, we could find the tangent line there at x equals 0. And we could graph that, and we can see that they're parallel. We say, okay, big deal, that's just Rolle's theorem. Well, yeah, but with the mean value theorem, it says, well, this still works even if you change the value of a. So let's make a like this. See how the whole graph changes just a little bit? Now when a is -2.9 and b is 2, the y value at -2.9 is -3.41. We could find that by plugging in -2.9 to this function. So 5 minus the quantity -2.9 squared happens to be -3.41 approximately. And we still have the y value of 1 when x is equal to 2. So our secant line is right here. And according to desmos.com, the slope of the secant is 0.9. They're just taking change in y divided by change in x and evaluating that for us. And they said, well, where is the x value? Where the derivative is equal to that slope of the secant? Well, the derivative is -2x. If I want to find the x value where -2x is equal to 0.9, I just divide both sides by 2. So the x value of interest, the x value we're looking for, is x equals the slope of the secant times -1/2. So it calculated that for us, and it gave us -0.45, or if you want, you can make it a fraction, -9/20. Either way, you can just press that little button on the side. And then the corresponding y value is right here. We can find that by plotting the point, or you can just evaluate the function at x1. And so we get that value. And if we draw the tangent line there, we see that the tangent line is parallel to the secant line, so the instantaneous rate of change is equal to the average rate of change. Now, I claimed that you don't just, it's not necessarily just one value. There might be more than one value. And that we can see from this example. I believe we looked at this example with Rolle's theorem yesterday. My makeup looks a little funny today, it does. So here's our function. Got all of these already graphed. And if we're interested in this function on the interval from -3 to 2, we have a Rolle's theorem problem. So we're just interested in this part of the function. At x equals -3, the y value is 3. At x equals 2, the y value is 2. So if I graph the secant line there, that's what I get. I get a line with a slope of 0. And I like to label what I'm doing on Desmos. And I just substituted this right here. I think I'm going to cut and paste that. Cut. And call that m secant. And say m subsecant equals that formula. Use lowercase m. Okay, they said you defined it in more than one place. Sorry about that. There we go. Thought I got rid of it. Okay, so the slope of the secant is this. The equation of the tangent line, or the secant line, is that. And so the claim is that there is at least one x value on the interval from -3 to 2, where the instantaneous rate of change is equal to this average rate of change. Since the average rate of change is 0, that means we've got at least one x value where the derivative is 0, or the slope of the tangent line is 0, which means that the tangent line itself would be horizontal. I think we can see that's probably going to be at the top here, and at the bottom here, we actually have two x values in that case. The way we find those is we compute f prime. We've already done that. It was 3x squared minus 7. Then you solve for x. Now that equation is going to have two solutions. X equals the positive square root of the slope of the secant plus 7 divided by 3, and then x equals the negative square root of the same thing. And so we get those two x values. We can plot those points. At that location, that's our positive one. The tangent line looks like that. And then at the top there, we have the negative value. It's the same. The tangent line looks like that. Say, okay, that's Rolle's theorem. What about mean value theorem? Well, you can just change the a value and the b value. Let's make let's keep a equals -3, and let's change b to, I don't know, let's make b equal to 3. Then we get that pretty picture. Isn't that neat? So in that case, the slope, if I let b equal 3, f of b in that case is 15. So then when we evaluate the slope of the secant, we're going to have 15 minus 3. So the change in y is actually 12. And then we divide by 3 minus a -3. So we divide by 3 plus 3, which is 6. So we have 12, a change in y of 12, and a change in x of 6. So we have 12 divided by 6 is 2. So the slope of the secant line in this case is 2. And then you say to yourself, okay, well, where is the slope of the tangent equal to 2? Well, you find the derivative. 3x squared minus 7, you set it equal to 2. Then you add the 7 to both sides, you divide by 3, and you take the square root. And it turns out that there are two values. So we have 3x squared minus 7 equals 2. So 3x squared equals 2 plus 7, which is 9. So x squared is going to equal 3. And then x will be plus or minus the square root of 3. And that's exactly what we get if we just use the formulas from before. The nice thing about using these formulas is, of course, they correspond to that particular function, or actually a family of functions that has that derivative. But once we've written down the formulas for all of the roots of that equation, f prime equals m secant, then as we change a and b, Desmos will automatically calculate the corresponding x values, as long as these formulas are correct. So we have these two x values, x equals plus or minus the square root of 3. And if we plot those 2 points and the corresponding tangent lines, so that point and that point, or that point and its tangent line, that point and its tangent line, we see that the tangent lines are parallel to the secant line. Now that's going to work for any interval that includes both endpoints. Now you might say, well, how might that change? Like, what is there ever a time when our equation would have two solutions, but only one of those is the solution on the interval of interest? And say, well, yeah, if this point was over here to the left of that local minimum, now we only have one x value that gives us the right slope. We would have had another x value down here, but that x value is not on the interval. The other x value that gives us the appropriate slope is outside of the interval of interest. So you see we don't get that x value until we go past that local minimum. And of course, we could do the same thing on the other side. We go past this relative max. We let A go past that relative maximum point. Now we only have one x value on the interval of interest. But if we keep A to the left of that relative max, we end up with that one and that one. But you see, it's really just Rolle's theorem. Look, there's Rolle's theorem. Well, approximately. I was trying to get the y values the same. This is 8.656, and that's 8.65 or 45. So it's very, very close. But Rolle's theorem just says that there's at least one x value where the slope of the tangent line is equal to the slope of the secant line. And the change in y for the slope of the secant line is 0 for Rolle's theorem. With the mean value theorem, we say, okay, well, what if the y values are different from each other? Well, then there is at least one x value, and there might be more than one. But the theorem says that there's at least one if that function is continuous and differentiable on the interval of interest. So that's how we do it with polynomials. One of the things that I don't like about Desmos is, at least right now, from what I understand, it doesn't have an equation solver, so I can't just say set f prime equal to m secant and solve for x. I actually have to do that calculation on paper or in my head and then type in the resulting x values. So I'm having to still compute this by hand. But if you had a more powerful computer algebra system, you could even just have the computer algebra system solve that simple equation for the x values. You might have one, you might have more than one, but again, you only keep the x values, or you're only interested in the x values that are on the interval of interest. But this little graph can illustrate that concept for you. So that's that. In the next video, we'll look at other examples. And those examples will include problems where the mean value theorem doesn't apply, and we can adjust the problem so the mean value theorem does apply, and equations that can't be solved by hand, where we might use a calculator or a computer to find the roots of the equation. So that'll be next time. Thank you so much. Let me know if you have any questions.